Alright, so music and science. And so here, just briefly about my science. So my science, this is what I do with my lab. I use laser. Not just laser pointers, powerful laser. So I can drill holes. And you say, what's special about this? It's actually drilled with this diameter of this circle is actually only the diameter of human hair. And that is very, very tiny. So it's just a simple, very small diameter we can do, right? And speaking of laser pointer, this morning I went to buy batteries for my laser pointer. It turned out to get 3 batteries will cost me $15. But I can buy a new one for $3 or 2 for $5. So I do what an Asian would do. I buy 2 new laser pointers. Alright, so quick outline. We start with talking about how sound is generated. It's due to vibration. So I'll talk about vibration, what is vibration. And specifically, we talk about the string vibration. Because that's how piano generates sound, how cello generates sound, how violin generates sound. And then we're talking into the music notes, how we decide the frequency, or how the music note gets decided, right? And then I would like to, this is sort of the big question I start out with, why some chord sounds good, and I would like to provide some scientific explanation to it. And then Olga will be showing 16 ways of hitting the notes. And then on this talk, we would like to see the music instead of listening to music more. Actually see how music behaves. And then she will continue to talk about music, language, and phrasing. And then we did some experiments to actually see how a finger touched the key and how key hit the bottom and what happened, right? And then how to avoid getting injured, right? All right, so vibration. Vibration means something is shaking, okay, either up and down or left and right, something is shaking. And the reason we can hear sound is because the air particle is vibrating. And when air particle vibrates, it compresses, it becomes a high pressure, or it can loosen up, becomes a low pressure. So, for example, if you have a speaker, Alright, so for example, you have a speaker, and the speaker actually, the diaphragm will be moving like this, vibrating. And then I'll push the air, and the air will propagate into our ear, and our eardrum will shake, and we'll hear the sound. Right? Same thing if I whistle, which I whistle all the time. And I always trap in a part of melody, I can never get through a song. And so this vibration, and usually we say, oh, we can describe it with science, and this is called a sine wave. And one quick thing to know now is, when we hear a sound, this represents the amplitude, how big it oscillates, and that related to how loud the sound is. And then how fast this oscillates, means within a second, how fast this oscillates will relate to the pitch. So that's the first thing we will know in terms of the sound from vibration point of view. So when we make music with piano, you see the key, and then the hammer hit the string, and then you see the string was vibrating. But when the string is vibrating, the string is too thin to move too much air. So we need a soundboard, and that soundboard moves a lot more air, and then you get a big sound. And then it would be really nice if young generations is crazy about piano music. So in science, the easy thing to do would be to say, well, how about this to do some little math to describe the vibration, right? So the simplest, the best, the purest form of vibration, we call it a sine wave. So the equation is very simple. It's just a constant which represents the amplitude times this sine function, 2 pi f is the frequency in hertz. Hertz means how many oscillations per second, right? And so if you vibrate fast, then the pitch will be high. So the typical notes that we say is 440, that's A440 is 440 hertz, is actually, the notes actually shake 440 times. So we can actually see that. So here I plot out the sound signal within 0.1 second, and we can actually count. So this 1, 2, 3, 4, 5, 10, 20, 30, 40, 44. And then times 10, that's 440 times. So that's what you have. A4 is 440 hertz. Okay. But we also notice this A4 note is not really looks a perfect sign. It's kind of has a little bit ripple up and down. And that means actually contain more than 440 hertz. It has some, we call it overtones, the harmonics, right? And so if you look at the harmonics, so we know the first harmonics, or the first overtone, second harmonics is 2 times, and then 3 times, 4 times, 5 times. And human ears is sensitive to about 20 hertz to 20 kilohertz. But piano doesn't cover that one, right? Piano doesn't cover. And all these overtones is the harmonics that make the notes sound good. If you only hear a pure sine wave at 440 hertz, actually sounds pretty bad. So I'll show you that. So this is the same. This is the A4 notes that we actually recorded. So let me play that. So that's the A. Okay, so that's A4 note. And if we strip all the harmonics, then make it into a pure sine wave at 440 hertz. That's a pure now. You can see it's straight, no little ripples, right? Just before and listen to it. Doesn't sound good at all, right? And then when you add more harmonics to it, it starts to sound better and better. So it starts to sound better and better, and then when it comes down to here, you got more harmonics, and this sounds closer to the original. It's not better than that, right? So we know those harmonics are important. The harmonics actually decided the difference of the sound we hear. Another question is, why the string will give you these different harmonics? Okay? Why string when you vibrate, when we hit the notes, and that string vibrates, and why that vibration give you that beautiful tone with all those harmonics, right? So this is called the string vibration. And I brought elastic for my wife's tailor work room. So here this is the string. It's a very elastic string, right? So can you hold it? Just a little demo. So if I quickly, you see this vibrates in many different forms, and that's what the actual piano string will vibrate. When you hit the hammer, it will vibrate like this. But if I hit it like this, right in the middle, then you see this is vibrating, the whole thing is vibrating, and that will be called the first mode, fundamental mode. And that will be the 440 hertz for that specific string for the A4 notes. Okay? And if the string is vibrating in this shape, it's something like this, and I can see if I can produce that. So if you probably get some ideas, it's not the whole thing shaking, right? It's kind of here, one half here, when the other half is shaking. And that will be called the second mode. And this will vibrate faster. This will not be, you vibrate twice as fast, at 140 hertz. So that will be the first harmonic, second harmonics. And then you can keep going, keep going, keep going. And so the actual string vibration will be containing all these modes and add together is a general vibration. And that gives you that nice, beautiful, rich sound. Okay? Here we got the cello professor is instead to actually demonstrate in cello when you push the press a different string and then you can generate harmonics. Okay, that's Professor cello.
Open A, half string, third of the string, quarter of the string, fifth of the string, sixth, seventh, and 1/8 of the string.
vibration mode of the string generates a specific vibration of the sound. And then each of them, you get it up, and then finally you get this, the total, the notes that we hear. That's not pure sine, that contains a lot of harmonics. And from science, I'm not going to go into detail, but there's a simple equation we can find out for a very elastic string, like a cello string. That frequency is depending on the tension and also density of string. So thicker string will be lower pitch, and higher tension and tighter will be higher pitch, and the length is most important. So longer string will be lower pitch, and if you half the string, and the frequency will be twice. It's just inverse to the length of the string, right? But piano string is a little bit different. Piano string is very rigid and tight, okay? So it actually, the second harmonics actually is not exactly 2 times. It will be actually slightly higher than 2 times. And we actually measured that to show you. So now, as I said, instead of listening to music, we would like to see the music more. So here is a typical playing by Olga. So you hear this beautiful sound, and then you see every time you hit it, you see the big sound comes out, and then you can see the amplitude gets bigger and bigger, right? And then damp down, and then function notes all together. So, and we can actually expand this, and then see the detailed oscillation. And again, the concept is how fast it oscillates related to pitch, and how big it oscillates related to the volume, right? So we save some time now. Great. And mathematically, we have a tool to take a music signal and actually kind of split it out and to find out what are the frequency harmonics contained in the music signal. So you see this a lot of oscillations. We don't know what are the frequencies included in this signal. But mathematically, it's for the Fourier transform. You can actually take it and then find out that each harmonics from the low to high, and then split completely, find out all the harmonics. So this is, we call it spectrum analysis. So we plot a chart, and the horizontal axis would be the frequency. So here, this is 440 Hertz, 880, 1320, and then so on. Okay, so we take that 440 piano notes, and then we do this spectral analysis, and we can plot out, and the vertical axis will be the amplitude. Okay, so now you can see the second harmonics. The first harmonics actually are normalized to be 1. So second harmonics in this case is less than 10% of the first harmonics. But since this came from piano, please notice for this piano, it's actually what? Tuned a little bit lower than 440. It's actually is 437. And then the actual second harmonics is 876. But if you take the first harmonics frequency times 2, it actually is 874. So that means what? Pianos, the second harmonics is actually a little bit sharper. And then the third harmonics is even a little bit more higher, right? And that's why when you tune piano, and I learned that from the piano tuner that I hired. So they have to tune a little bit sharper, because when you tune A4, you have to match the second harmonics of A5 has to match the second harmonics of A4, otherwise it doesn't sound good. So you see, in the higher key, it just tends to be sharper and sharper, and the lower key has to be kind of flat and flat. Right? It's not perfect straight. Right? That's the piano tuning. And I think, well, I guess you have that experience when you accompany somebody playing the violin or cello. I think the cello player or violin player has to kind of play a little bit sharper, right? I guess that's what's happening. I cannot play, so I don't have that experience. All right, and then we also realize different instruments, they have different color. It's because all these harmonics looks different. So we actually measured 2 pianos. One is the Bosen-Doepfer, and one is the Mason-Hamlin. And now we look at its spectrum, and we realize the high harmonics may be quite similar, but the second harmonics can be quite different. So the second harmonics probably is most critical in determining how an instrument will sound. And from there, we kind of finish the first topic, and now pass on to Olga to talk about how we actually decide the music notes.
The fact that we have 7 notes, or we divide the octave in 12 parts and we have the semitones, is actually a product of human intuition. So the 7-note scales existed much before, the science kicked in, and scientists try to explain and try to notate and have some record of the notes. So you get 7-note diatonic scales in any kind of culture. African music, even in Middle Eastern music and in Far East music, although China, that part of the world rather uses pentatonic scales, but you still get those 7 notes. And the explanation of that is again science. It's actually our brain. Our brain perceives algorithmic increases. So the distance from one key to another, or from one note to another in diatonic scale, is an algorithmic, ratio, which is pretty much constant. That's why our ear picks it up, and that's why the scales that were theoretically designed, scales of 24 and 48 notes, actually did not, find their place in oral tradition. So Pythagoras in 6th century BC was the first person who sort of, well, actually he was not the first, but maybe for Western music, he was the first one who made a record of organizing the pitches and coming up with some diatonic scales. So what he did, he noticed that the ratio 3:2 of 2 notes would sound good. And of course there was no way to measure frequencies at that time. So he came up with a system where he just goes, he has 12 consequent pitches in the ratio of 3:2, and that way we actually get this circle of fifths, and I'm going to play it for you now. So let's say he started with middle C, and then so you get 6 notes this way, and get 6 notes that way, and then he moved them back to the same range by using ratio 2:1, by moving them back in octaves. So he came up with this 7-note diatonic scale. And if, on the Greek lyre, if you use these notes, you get Ionian mode, you get Dorian, and then you get Phrygian, right? Lydian, and all the ancient Greek modes. So that probably a way to use different scales was using different modes with the same 7 pitches. But when it came to actually transpose, to move C major one note higher and use D major, it was impossible, because in Pythagorean tuning, fourths and fifths and perfect intervals and a major third sounded right, sounded good, it was a perfect ratio, but then seconds didn't really sound good, and when musicians wanted to use scales like D major, it didn't work. So up to the 16th century, musicians were experimenting. Just imagine, from 6th century BC up to the 16th century, musicians were experimenting with the tuning system. So there was mean-tone temperament, where they adjusted the tuning for the thirds. And that mean-tone tuning worked well only for major scales and didn't work well as much for minor scales. That's why, for example, in Bach preludes and fugues, we still have some in minor scales sometimes. In minor keys, sometimes we end with major, right? And that pretty much actually determined the use of the major fifth in minors. So there was mean-tone tuning, and then there was well temperament invented by Andreas Werkmeister, who was Bach's predecessor, and he was an organist and tuner. So Werkmeister came up with a system which was a little bit better than mean-tone tuning, where he, for example, used the same tuning for F sharp and G flat, and he came up with a system where it was a frequency somewhere in the middle. not too high for F sharp and not too low for G flat and so forth. And then actually in the 16th century there appeared a new tuning system, equal temperament. And it was already invented before musicians started actively using it. It was the father of Galileo Galilei, Vincenzo Galilei. He said, well, how about just dividing the octave into 12 equal parts and using that tuning system? Well, it worked fine, and there were some musicians who used that system, and there were works written, but it didn't really come into active use until the 17th century.
Okay, that's all I just explained. When we go from A4, which is 440, to A5, 880, and in between you got 12 notes, then we don't just divide by 12, so each one is like 440 divided by 12, so each one is about 40. Doesn't work down. And so what it actually works is, so every note you increase by a specific percentage, and it turned out to be you increase by 2 to the power of 1/12. And then after 12 steps, you go to 2 times, right? And if you calculate, it's similar to from A4 sharp to A4 is increased by 6%, roughly about 6%. And then next note will be increased another 6%. So think about is the money growing in the bank, and you have a monthly interest rate of 6%. So you start with $100, at the end of the year, you got $200. Gee, we'll get real rich. So I think that's the best way to think about how the music notes change in frequency. It's just 6% from the previous one, 6% from the previous one, right? Just keep growing, keep growing. In that way, when you go into the next octave, that will still maintain that proper ratio. One octave will be 2 times, everything works properly. If you just divide it, it's not going to work, right? Because next time, the 840 plus something is not going to be 2 times of 440 plus something. And now, the question is, when we actually do that increase by about 6%, we don't get that exact integer ratio, right? And so here, from C5 to G5, that's fixed. And usually we would like to get 3 to 2, that's 1.5. But actually, with this tuning, it is 1.493, close enough. I don't know how, I just run it off as close enough. But our ear is actually quite sensitive. It's amazingly sensitive, right? And so some people claim if you tune this way, it's not a lot better. If you tune this way, it's okay, it's a compromise. Right? But I cannot tell. You guys can, I cannot, right? And then same thing here, you got this will be fourth, it's 4 to 3. And then third, this is 6, C to A, 6. It's 5 to 3. And then this is third, will be 5 to 4. So 2, 3, 3, 4, 4, 5, and then 3, 5. And then if you just from C to D, it will be 9 to 8. But if you tune it with all these integer numbers, it's not going to maintain. Because if you just go from this to this, and you use that integer ratio, then you got 1.48. And that's all. Okay, that's all. And now, I try to use this to think about why some chords sounds good, some chords sound bad. And it seems to me the reason there's a chord sounds good because harmonics match, right? So the perfect match would be if you have a C and C4 and C5, and it says second harmonics which is twice, and then C5 is twice, and so they match perfectly. So that's the best match. But if you have a fifth, then it turns out to be the second harmonics of G will match the third harmonic of C, and so there's also a match. There's something not matched, but you have something matched, so that will sound good together. It seems to me that's not the way. And then the third best match will be the perfect fourth, and some honorable mentions 6 and 7s, right? And but when it doesn't sound good, what happens when something doesn't sound good? And we always say, okay, let's talk about this first. So here, if we have again, I feel so uncomfortable to talk about this. All right, so this is how do you call it? 1. Okay, 1. And then 4 and 5. All right. So the ratio turned out to be 4 to 5, 6. And then now you know the fifth harmonics of this match with the fourth harmonics of this, or third harmonics of this to match the second harmonics of this. So there are some good matching here and there, right? So when the chord comes together, they just have some good matching with those harmonics, right? And we can actually plot it out. So I can plot it out to show you. So I take C, E, and G, and then plot out all their harmonics. And then there are a lot of matching. So here match, and here is match, here is match, and this match. They all have several matching. And then our ears just say, oh, okay, there are a lot of agreements. So in the room, people talk nicely and say, yeah, good, yeah, they don't fight, and it just sounds good, right? And, but here it didn't show, the projector here didn't show. Actually, I highlight this in the shade, but I didn't show here, so you didn't see this all the matching part, right? But what happened? What happened if we always said, well, close but no scar? You are almost there, and always I hate that when people get second place. They say, "Oh, you're not a winner." Hey, second place is so good. But this is what happened. Sometimes we have a match, but it's not perfect match. Slightly off. Okay. So, for example, these are the G notes, and there is harmonics. That's plugged in blue, and this is B3 notes, and this harmonics plugs in green, and then D sharp plugs in red. And then F4 and plug this harmonics plugs in this silent color. So you can see this and this almost the same, but not quite the same. They don't quite match, right? And so you see something here, the same thing. They are close, but not quite the same. This and this close, but not quite the same. If they are far apart, that's fine. The problem is they are almost there, but not quite. Okay. So what happened mathematically? And this is what happened because now we have a beat phenomenon. So this is the actual recording we did with two pianos in her office, and they are tuned slightly off. So we hit the same key on both pianos, and then you start to hear this sort of beat phenomenon. So we can listen to that. So you see start to ring at the end, and then we can actually see that. You see this start to ring. Gets bigger and smaller, bigger and smaller. And I don't know if you can see here, and that's when we do the maths, actually the signal just gets bigger and smaller, bigger and smaller, bigger and smaller. It's no longer uniform. And why it actually will work that way, and this is called a beat phenomenon. So if you take two sine waves, they are very close, but not quite exactly the same frequency, and you overlap them. So the sound add together just like math, just addition, just add together, right? So you can see when they perfect match at this instant, then the amplitude doubles, so it's a big amplitude. But then after a little while, and they are the opposite direction, one goes up, one goes down, then they cancel each other, become zero. And then somewhere in between, it just goes down and big. So you have two notes, they are very close. And then when they add together, you start to hear ooh, ooh, and that's a beat phenomenon. And it seems to me this beat phenomenon is the one that makes us uncomfortable. And so if you have a chord that will cause a lot of those harmonics, they are close but not quite the same, then you have a lot of these beats and you don't feel good. Okay? So let's see if that's the truth in terms of harmonics analysis. So here this is G. Okay, it's beyond. And now we look at all the harmonics. There are some good matching, and then I highlighted, but you couldn't see it on this projector. But then the cross, I put in this big cross, is all those that's close but not quite the same. And so you see a bunch of those close but not quite the same. And so these chords, according to musicians, not me, to me, those sound the same. and this doesn't sound good. So this probably makes sense, right? So this is probably trying to provide a scientific explanation of why some chords sounds good, some chords sounds bad. And then in terms of tuning, that's also important in the orchestra. We all know that. I mean, everybody has to play the same tuning together. Otherwise, all this beat phenomenon will happen, right? So I guess from here, we talk about how actually you control the sound to generate music, and that's the other.
So initiation, right? And then the way we have our sound waves, and then the way we end the sound. And it seems to be very important when we talk about the musical phrasing. And with piano, it's particularly difficult because we have this percussiveness at the beginning, and as a rule, the sound initiation will always be big, and then we say that the sound decays, but actually there is some growth in the middle there. So when we do our phrasing, and we experimented, actually we had only 16 ways of hitting a key, and we recorded, and then we compared, and here is what we've got. So we had Jay play piano and me play piano.
Non legato note in forte. Loud, non-legato note played by a beginner.
So this is what we get. Just comparing the sound wave. My sound wave is longer and it sort of develops. Jay's sound wave is a little bit shorter. But look at the second harmonic here. So it seems that the second harmonic is somehow responsible for the quality of the tone that we get here. See? All the rest of the harmonics are different, but probably we get second harmonic significantly bigger when the sound is brighter, rougher. I would say brighter. Then we had non-legato with pedal. And here in green, can you see the sudden stop here? So Jay dropped the pedal, and you can see that. Yeah. And here the note 3 nicely. So here we want to see.
Non-legato loud note with pedal.
When we actually compare the pedal without playing with pedal and playing without pedal, we can see that the second harmonic is enhanced 5 times. It's huge, and it somehow makes our sound brighter. So it's again second harmonic at fault. And then we have non-legato. In soft non-legato, it seems to be very close. And then here, in staccato again, look at the second harmonic just spikes. And here, and here the fourth harmonic is also. All of the harmonics here are bigger. And I think it's because the sound is stronger and brighter in the way Jay hit the piano.
Staccato note.
This one has a strong gain. And this one, sorry.
Staccato note.
So they're almost the same. When we actually compare, the tone quality is different, and we can see that on the chart. And then here, this one is funny. So we played a chain of just long notes here, and we tried to play. So see, I really worked hard on trimming the sound towards the end, and of course it's very difficult. So when we get the student play, you can see. So we can actually see what happens. Here is an experiment that we had, and I chose Tchaikovsky on purpose because this beginning seems to be a very difficult opening phrase for students. Maybe the reason is that you get to play the phrase with your thumb 3 times, and of course students have difficult time controlling their positions, shifts, and you usually get the accents in that line. It's very difficult to make. So I use two ways of playing, and we can see the good one, or the better one, and then the worse one. So this is probably how a student would just play. And then you get percussionist. So it is very, in phrases like this, it's very difficult to hide the percussiveness, the percussive initiation of the sound. And we really have to work hard on attacking the key slowly and getting the sound grow gradually. So, and that's what I would show to my students, that if you don't try hard, then you get initiation for every note that's very different. And we can compare, for example, piano playing to cello playing exactly the same tune. And look how the sound wave looks like. Right? So with cello the sound grows and decays, and with piano we always need to adjust the level of the initiation in our musical phrase. And when we look even closer, when we zoom, here's the difference. So with the good legato, we get a little bit of overlap here, and we get a smoother connection. And with bad legato, the connection between the two notes would be, just different. The second note would appear to be bigger. And the same thing we can say about the accompaniment. So every element in our playing has to have some kind of like smooth lines and development. So when we play the accompaniment, we also try to make some kind of wave. Like for example in Beethoven Sonata Number 9. So that's how that accompaniment will look as a sound wave. We try to have the three chords to be dynamically close to each other, and then if we want the phrase, we need to develop again dynamically those chords to have certain shape and then trim at the end.
So you saw earlier that when I hit the key so badly, but if you pay attention, on the piano key there's a blue wire, and that's a sensor we actually mounted on the piano key, and that sensor is called a accelerometer. So that's I draw here. So this is a grand piano key mechanism, and so we mount the sensor right here to measure how the key will move up and down when a player uses his finger to hit the key. Right? And when I measure this will be acceleration. Okay, acceleration. When you drive a car, when you stop and then you on the gas pedal, the car goes, and that's acceleration. And then after some time, you pick up speed. And then after some time, you move the distance. So mathematically, you take acceleration, you take integration of acceleration, you get velocity. And then you take integration of velocity, you get displacement. Right? So that's what I do. And so I take the measurement of the acceleration down here, and we don't worry about the units. And here is in second, right? Don't worry about unit. So this will be when you hit the key, and now you see some key will oscillate and some acceleration. And then you let go of the key, and that's what happened here. The key also gets acceleration. Then I integrate to get velocity, and then integrate again to get position. So here position will be clear to you. The key got hit down and hit the bottom, and the bottom shakes a little bit and stay in the bottom. And then you let go of the key, and then it comes out and shake a little bit instead. Right? So the key goes down, it comes back. Right? It comes back. But if you look closely in the very beginning, and that's what gets interesting, at least for me. And here, if we look much closer in the very beginning, that's when the finger hit the key and you push down the key with acceleration, a downward acceleration. And with that, the key starts to move down. And then it hits the bottom. And when it hits the bottom, boom, the key actually has a huge acceleration going up. And that's the impact when you hit the key bottom, right? Another question is, what this means. And I also believe this impact when you hit the bottom will affect your sound. And so we do a little bit of analysis here, and this will be a simple, we call it a Newton's second law. So what happens is F equal to ma, and F actually is a summation of all the forces together equal to the mass times the acceleration of the key. So let's say this is the mass of the key, and this is the acceleration of the key. So initially, when we hit the key down, we only have the finger force acting on it. This will be 0. So now we have this acceleration. So this F1 equal to ma. So that'll be right here. But once you hit the bottom, now there's an impact force. Right? So now the bottom will have a force hitting back. And that force, the F1 and these fingers still have force, and the difference becomes acceleration. Now the question is, if you hold your finger really firm, then this force will be big, and this is always big. So big minus big, and you actually end up being not too big. Okay? Not too big. Then this acceleration will be small. Is that better that way, or you make your finger kind of relax? So you don't really try to hold the key down, you relax, and so you let the key bounce out more and more acceleration. So is that a better way? And how that will affect your sound, okay? And so we do a comparison. So this one, the blue is, she hit it, and then she said, you relax your hand right away and absorb the shock. So hands relax, let the key bounce out. So you got high acceleration, key actually bounce out. And the red one is for the stiff hand. You hit it down and then just hold it firmly, and then you prevent the key from going up. So now you have small acceleration. But small acceleration means what? It means you have big force acting on your finger, and that can hurt you. So you hit it hard, and then so now maybe kids start learning, and they might end up hurting themselves if they don't learn that relaxing motion. Once you hit a key, you don't relax, and the measurable shows there's a lot of force hitting back by the piano on your finger, and that chain reaction. And so a player can get injured, right? And the other thing we also notice is, if you relax your hand, you let the key at the bottom actually bounce a little bit longer, and before it settles. And, but if you hold it firm, then of course it quickly settles. The key just doesn't bounce as much. And we also compare that to staccato, right? So again, it's non-legato and this staccato comparison. So in the legato, you hit it down and the key just stays down. And legato, you hit it and then you immediately bring it up, like boom, and then let go. And so the key actually comes up. And then in the legato, actually, you also have less acceleration. That means what? Your hand didn't have time to relax. So there's more force. When you hit the staccato, there's more force acting on your hand by the piano. And then we actually look at the time. I think the overall time when the key starts to go down and then comes up, and it stays down about 0.05 seconds. That's pretty short. But altogether, this time interval is 0.14 seconds. That means what? It's if you have to hit the repeated notes, I think physically you are limited to 7 times per second. And I don't know what's the world record. But physically, this definitely you cannot go beyond 7 times per second. But if you have 2 notes, probably you can try to match that, but not 1 note. Not 1 note. So I think with this, I'm done with my science part, and I did Olga finish it up.
So I think when we talked with Jay, we discovered this aspect that there is this reactionary force acting on your hand once you hit the bottom of the key. I was actually, it completely changed my, my teaching style, or maybe I just started implementing it right away. But it actually hit me that whenever we play fast passages, if we don't take a ride on that second force pushing you back, it really puts a lot of burden on our fingers and our hands and our body, and we get tired. But a very natural technique is actually when the pianist takes a ride, when the key goes up, and that helps the pianist move to the next key. And the fast passages, when you see somebody just throw the hand and then play it like 60 notes in a few seconds. So that's probably the secret of using the instrument properly and knowing the limits of the instrument and also knowing the limits of our body. The connection between music and science is deeply profound. And in some respects, one helps another evolve. For example, we wouldn't have music develop beyond the oral practice if we didn't have, mathematicians discover the connection, the musical pitches, the tuning systems, and then if we didn't have musicians develop those tuning systems, and then instrument builders, come up with highly advanced instruments like Rachmaninoff third piano concerto wouldn't happen if somebody wouldn't have built the piano, right? And for today, I will leave you with this quote that is an inspiration to this project from Einstein. So he said that the theory of relativity occurred to me by intuition, and music is the driving force behind this intuition. My parents had me study the violin from the time I was 6. My new discovery is the result of musical perception.